Hi, I'm Jim Heffron. These are my lessons in Calculus 1. So very exciting. We're starting in a new chapter, and in fact, we're starting in on a new topic entirely. This Calculus 1 class has two big topics. The first is differentiation, and the second is integration, and we're starting in with integration. Before I start in, though, just want to make a comment. The book does something that I don't think is right. I usually try to stick to doing things the way the book does them because why confuse people? But in this case, the book does something. They put anti-differentiation in the section on differentiation, and I just think conceptually it belongs in this section on integration, the section that we're starting today. So I've put it there. Okay, then one more thing I want to say is that we're going to do sort of a lot, kind of chunk together a lot here, and so I'm in fact going to just bow to the practical reality that people need to practice between doing things, and I'm going to break the slides from today into two parts, kind of a 5.1a and a 5.1b, and everybody has their way of doing things. This is just my way of doing things. Okay, great. Let's get started. Let's see. So there are there's the picture that we saw on the sort of first introductory day of these lessons. So Tycho Brahe made very accurate observations of the night sky, and then Johannes Kepler was his assistant. He used the numbers to produce the three laws that the planets follow, and of course Leibniz and Newton accounted for those three behaviors using only the single assumption that gravity falls off with the inverse square. And to do that, Leibniz and Newton needed to solve the two great problems of calculus. The first problem is to, for instance, find the velocity of a planet. So there's a planet moving along its orbit. That's the rate of change problem. And we've been working on that for, probably it's 2/3 or 3/4 of the course. So they developed a derivative for that. But we're now going to tackle calculus's other great problem, which is the accumulation problem. Kepler's second law, for example, is that planets sweep out equal areas in equal time. I'm going to show a planet sweeping out, areas in 10 days. So you look at the line that connects the planet to the sun, and it sweeps out an area. At each instant, the planet's moving at a slightly different rate and in a slightly different direction. So you just can't take one of the slices and multiply by, or that doesn't work. What's being swept out changes from instant to instant, and there's infinitely many instants. So in grade school, we learned how to accumulate together discrete quantities. 3 apples plus 2 apples makes 5 apples. But we're now going to cover the accumulation of continuous quantities. This is often called the area problem. You see why? Because on this slide, we've got an accumulation of area. I have a comment here before we get too far into it. So when you start a new topic like integration, it can be that the threads that you need to make a first sense of the topic don't fit inside the time needed for a single lecture. So we have 3 different threads, antiderivatives, Riemann sums, and definite integrals. You don't know what those words mean yet, but fine. But I have to put together 3 threads, and although I'm going to do some motivation to reduce the dissonance, the parts won't make a coherent whole for a couple of lectures. All right, just a question of the time traditionally left for a lecture, something like 50 minutes, or if you do some homework questions, 35 or 40 minutes. It just simply isn't enough. Okay, so I apologize. I hate it when I go to a lecture and I don't understand why we're doing what we're doing. And so I try to make it so that happens at my lectures as rarely as possible. But this is a case where there'll be a couple of days where a person doesn't really feel they have their feet under them. Okay, so first thread, anti-differentiation. Here I have I'm going to start with a one-dimensional accumulation problem. So I have a relay runner who's covering the distance, and we know the relay runner's velocity function. Do you see that the velocity starts at 2, not at 0? I needed a relay runner for that because they have a running start. I want to know, given their velocity, I want to know their position function. Okay. So first of all, this is an accumulation problem because if you looked, for example, at time equals 2.51 and time equals 2.52, there is some tiny change in position that we're going to accumulate together all of those tiny changes in positions, all of those infinitesimal lengths to make the total ending position, all right, P of t. So I'm accumulating them all together, and how do I know how much there is at any instant? The answer is the velocity, v of t. Second, we can also view this as an area problem. So I got a graph there of v of t equals 1/2 t plus 2. 1/2 t plus 2, that's this function right here. And the shaded area runs from t equals 0 to t equals x. You see the x there? T equals 0 to t equals x. Do you see that that's the t-axis and the v of t-axis? The t-axis units are in seconds, and the v of t-axis units are in meters per second. So if you look at any one box, you're multiplying seconds times meters per second, so that box is a meter. So if we find the formula for the area underneath the curve between t equals 0 and t equals x, why, then we have the position in meters. We know the total number of meters accumulated. But this is a high school problem. There's a triangle and a rectangle. See, this rectangle is too tall, too tall and x wide. And this triangle here is, again, x wide, sort of stuff. So the rectangle plus the triangle is the rectangle plus the triangle, 1/2 base times height. And when you do the algebra and combine them together, you get 1/4 x squared plus 2x. So the velocity function is v of t, and the position function is p of x. I know they have different letters, but we were able to figure out from the velocity what is the position. Third, we already know how to go from position to velocity, namely take the derivative. So we can view the problem of going from velocity to position as antidifferentiating. Indeed, if you think about it here, the 1/4 x squared plus 2x that I just got a minute ago, if you take its derivative, you do indeed get the velocity position that we started with. I know I changed the letters on you, but I really wanted to have an x there. Okay, so there's something involved going backwards. We're starting with something that we view as the derivative and going to something that we view as the thing it came from, the antiderivative. So that previous slide shows a link between accumulating, finding area, and antidifferentiating. So here, for example, if I look at the region below the function's graph and above the axis, this region in here, okay, what we will think about doing here is we will think about accumulating that area. So we will think about sweeping from left to right here, sweeping from left to right, and accumulating together all of the area we're interested in. So we accumulate that area by sweeping from left to right. We call each, sorry, hit the wrong button. We call each of these red columns a slice. We'll call that a single slice. So we accumulate together each of the slices to make the yellow area. We say that we've integrated the slices together to make a whole. So it's almost like you had a movie of someone slicing bread and you ran it in reverse. You stick all the slices together. Leibniz had in mind that each of those slices contributes to the yellow area at infinitesimal area, and the total area is the infinite sum of all these infinitesimal summands. So his notation uses a capital letter S. Capital letter S applied to the infinitesimal area of each slice. So if you look at a slice like so, it is f of x tall, and it is dx wide. Can you see the dx there? Dx wide. So there's f of x times dx. That's the infinitesimal area of that slice in Leibniz's mindset. And so he's got a sum. So he uses the letter capital S to represent accumulating together all of those infinitesimal things. That capital letter S has gotten a little stylized over the years, but we're going to use it to denote the antiderivative operation, the direction to find the function whose derivative is the given one. Okay, so the definition is you start with a real function lowercase f defined on some interval. Then an antiderivative is a function capital F, where capital F prime is lowercase f on that interval. And the first point about antiderivatives is if you start with I just started here with a familiar, not very hard case, and I said let's look at 1/3 x cubed plus 2x, and right away everybody has so much experience with derivatives. Everybody says yes, indeed 1/3 x cubed plus 2x does indeed have the prescribed derivative. And you say I see how you got that. You started with x squared, and you say well the antiderivative, the thing whose derivative is x squared, is going to be some kind of x cubed. But x cubed itself won't work. You need somehow, because if you took the derivative of x cubed, it would be 3x squared. So you put a 1/3 there to counter the 3 and you're good. And likewise, you want to find somebody whose derivative is 2, so you said 2x. But when you go over to f2, it's 1/3 x cubed plus 2x, a repeat from the previous one, plus 1. Ah, that's right, because when you take the derivative of the plus 1, it disappears. And likewise here, minus 2/5. The derivative of the minus 2/5 would also disappear. So in fact, there's infinitely many functions whose derivative is lowercase f. Okay, so the first point about antiderivatives is that you get a family of answers. You might recall this result from the mean value section. The mean value section, I think, strikes a person as a rather theoretical, but we need it right now. This is the moment when we need to pull out that corollary. F and g are real functions that are differentiable on an open interval from a to b. If f prime is equal to g prime for all inputs, then f minus g is constant. So functions with the same derivative differ by a constant. That is, on open interval AB, there's a real number, capital C, where f is equal to g plus capital C. Okay, now that was in the mean value theorem section. We need it right now. That's why we did it then, because we need it now. I'm going to restate it. We didn't have the word antiderivative at the time, but we have it now, so I'm going to restate that corollary in terms of antiderivative. So you're looking at a real function f defined on an open interval AB. On that interval, if capital F is any particular antiderivative, then all antiderivatives have the form capital F plus capital C for some real number, capital C. So capital F plus 7, capital F minus 4, capital F plus 0. Those are all antiderivatives. We denote the operation of antidifferentiation, of finding all of lowercase f's antiderivatives, with the indefinite integral symbol, and of course we use the symbol there, and in some ways it serves as an open parentheses, and there's a dx over here. We talked about that a little bit with Leibniz too. In some ways that serves as a closed parentheses. Okay, and then the capital F plus capital C represents a family of functions. So capital F plus 1, capital F plus 2, capital F plus 3, capital F plus 17.9, capital F minus pi, capital F plus 0. That's a family of functions that are related, but nonetheless infinitely many different functions. Okay, and of course, high time for practice. So I'm just going to ask you to look at each of these ones and say, what function is it that has the given thing for the derivative? Here, what function is it that has x squared plus 2x plus 4 for the derivative? And I'm asking you to provide all of those functions. So you're going to need the capital C. Okay, and of course, I'm going to ask you to pause the video, try it, and come back. And even if you get stuck, the fact that you got stuck gives you some leg up because you thought about what it is that is causing you to get stuck. Okay, here we go. Okay, great. And in order to have a derivative of x squared, you have to be some kind of x cubed function. And x cubed itself won't do because the derivative would be 3x squared, so it must be 1/3 x cubed. Likewise, in order to have a derivative of 2x, you need to be x squared, and in order to have a derivative of 4, you need to be 4x, and don't forget the plus capital C. That includes the plus 0, the plus 1, the plus 2, the plus 3, and the plus pi, and whatever other. Okay, next one, please. Oops. Okay, so with this one, sorry, hitting the wrong buttons. So with this one, you're just asked to remember here that that a radical is really a fractional power. Then in calculus, the easiest way to write fourth power is to write it as the 1/4 power. So the fourth root of x to the fifth is x to the 5/4 power. It's just simply in calculus the easiest way to do the job. So how are you going to have a derivative of x to the 5/4? Well, you must be some kind of x to the 9/4. Because when you take the derivative, you're going to end up subtracting 1 from that power, and 9/4 minus 1 is 5/4. But if you took the derivative of 9/4 itself, you would, of course, have a 9/4 in front. We don't want a 9/4 in front, so to counter it, we put 1 over 9/4. And please, I know that 1 over 9/4 is 4/9, but I put it as 1 over 9/4 to make a point. Anyway, I wrote what I wrote. And don't forget the plus capital C. So the answer is 4/9 x to the 9/4 plus capital C. Okay, next one, please. Okay, great. I mean, the great thing about e to the x is the derivative of e to the x is e to the x. And so saying it in reverse, the antiderivative of e to the x is e to the x. So you just get what you get, and don't forget the plus capital C. Number 4 is a little bit tricky there, a little bit tricky. Now, we don't have any kind of chain rule set up. So x minus 5 squared, as people who are taking an awful lot of derivatives, we think to ourselves, there's some kind of composition happening there. So I'll give you a second to think about it. And the answer is that yes, indeed, there's some kind of composition happening there. We don't yet have rules for what to do in composition cases, but you still could square and then antidifferentiate the square. So that's what I did. I squared it out, x squared minus 10x plus 25, and antidifferentiated to get the 1/3 x cubed, the minus 5x squared, and the 25x. Okay, so how do you have a derivative of 10x? Well, you got to be some kind of x squared. Which x squared? 5x squared. And don't forget the plus capital C. And then the last one. Okay, great. Do you remember what function it is that has a derivative of secant tan? It's secant, yeah. So some of these things a person has to remember. And of course, that's why we keep going back and looking over old problems so that it's fresh in our mind. Before we go on, sometimes people get the impression, for very good reasons, perfectly natural, that C is just something you add to get the same answer as the back of the book. That it's just some annoying formality, but that's not right. That C has a meaning. In an individual problem, we might not talk about what it means, but nonetheless, C has a meaning. So I want to focus for just 10 seconds before we get too far from introducing C on how a person can interpret what it means. So I have a physics problem. We throw a ball upwards with an initial velocity of 4 feet per second from an initial height of 432 feet. So here I am on the top of a cliff. 432 feet in the air. And I throw a ball upwards, and of course eventually it will come down. So the acceleration due to gravity is 32 feet per second. Oops, I made that in italics by accident. 32 feet per second squared towards the Earth. Find the formula for the height above ground at time t. Okay. So of course I'm given here. I'm given the acceleration. I know that the acceleration is minus 32. And because that equation that says the second derivative is minus 32 involves derivatives, it's called a differential equation. So I'm given the differential equation. I want to go from acceleration to velocity. So I take the antiderivative. Antiderivative of minus 32 is going to be minus 32t, and don't forget the plus capital C. And I want to talk about what capital C means. That's why we're here. So use the initial condition. Use the initial condition that you threw the ball up at 48 feet per second. That's in the direction opposite to the Earth, so that's why this is minus 32 and this is plus 48. But anyway, use the initial condition that you threw the ball up at 48 feet per second. If you plug in 0 to both sides of this equation, you get V of 0, which we know is 48, is equal to minus 32 times 0 plus C. So V of 0 equals C. So in other words, V of t is minus 32t plus 48. So capital C means 48 in this problem. It has a meaning. It's not just some formality. I'm going to emphasize that by doing it again. So I'm going to go from the velocity to the position. So I took the velocity function here and took the antiderivative to get the position function. To have a derivative of minus 32t, you're going to want to be minus 16t squared. To have a derivative of 48, you want to be 48t. And then I called it capital C hat because I didn't want to use capital C twice in the same problem. So the same idea works here, is that to fix the value of capital C hat, you use the fact that P of 0 is 432, and you plug 0 into both sides of the equation, and the 16t squared cancels 48t, and you're just looking at C hat equals 432, so you get the position function. So again, the constant of antidifferentiation has a meaning. In a particular problem, of course, we may or may not give it a meaning, but nonetheless, it's not just some formality, something that you have to throw in to get the right answer. It has a meaning. Okay, anyway, that leaves me with the formulas that a person would use to do the homework here. Every differentiation rule, for example, that the derivative of e to the x is e to the x, is an antidifferentiation rule. So for example, if you want to say who has a derivative of cosine of x, the answer is sine of x. Who has a derivative of sine of x, the answer is minus cosine x. And this one up here is probably the most familiar one here. So if you want to, for example, say who has a derivative of x to the 8th, why, it's going to be some kind of x to the 9th. Don't forget the plus capital C. But x to the ninth itself would give you a derivative of 9x to the eighth. That's not what you want. So you say 1/9 x to the eighth. So that explains the 1 over n plus 1. And then the differentiation rules about moving out constants become antidifferentiation rules. If you want to find the antiderivative of 12x squared, that's 12 times the antiderivative of x squared. And likewise, you can break along a plus sign or break along a minus sign just as you do with derivatives. Okay, so every differentiation rule is an antidifferentiation rule. One of the good things about taking antiderivatives is that if you think you found an answer, you can check it very easily. You just take the derivative. So if, for example, you think that someone whose derivative is ln of x is this expression, you've been walking around for a while, well, if you take an x there and subtract it off, that will cancel just take the derivative of both sides. So the derivative here of x times ln of x minus x, plus capital C, the derivative is very easy. We've been taking derivatives for a long time, and it all cancels and just gives you the ln x that you wanted. So it's easy to verify when you have a candidate for antiderivatives. It's easy to verify. Just take the derivative. There's very much less in the way of I wonder when you're taking derivatives. You spend a lot of time with derivatives just following the rules. Here's one more. So I'm going to worry about how do you take the antiderivative of 1 over x for negative x's. We know that the antiderivative of 1 over x for positive x's is ln x. What about for negative x's? And so you walk around for a while saying, what to do, and you come up with this. Can we check, please? So the derivative of ln of minus x, here's the derivative of the ln part, here's the derivative of the minus x, and sure enough, the minuses cancel and you get 1 over x. So that's right. Okay, so if you have a candidate, it's easy to check. A couple of comments about antidifferentiation. The first is that taking a derivative is, there's a contrast. Taking a derivative is straightforward, although intricate. It took us a while to learn it, but straightforward computation. But finding an antiderivative has some of the quality of doing a puzzle. We'll see some techniques, but sometimes it's just down to a certain amount of cleverness. And one more comment. So in this class, we work with a certain kind of functions. You have formulas that involve adding, subtracting, multiplying, taking the square root. We'll work with trigonometric, hyperbolic, and exponential functions, and maybe inverse trig functions, etc. All the stuff that a person runs across sort of in elementary physics, elementary chemistry kinds of functions. Those are called elementary functions. So I'm going to note that there's an advanced result that we won't cover in this class, but we'll mention it from time to time, that there are elementary functions that don't have an elementary antiderivative. So for example, e to the minus x squared, it looks like a perfectly innocuous function and you wouldn't have any trouble taking its derivative. But if I asked you to find the function whose derivative is e to the minus x squared, you'd be walking around saying, well, if I take the square root, and you'd never find it. It's not just that nobody has ever found it, it's that we can prove you can't find it. The antiderivative of e to the minus x squared does not have this quality. It is not one of these with that collection of functions. Just to give a second example, another example of the same thing is the square root of 1 minus x to the fourth. So one way to say that something is hard is to say that it borders on the impossible. And I also want to caution you, sometimes when you do a motivation section, you're a little nervous that people walk out of the motivation section having missed some points. So we talked about that the derivative of, the integral of a sum equals the sum of the integrals, and the integral of a difference of a subtraction equals the difference of the integrals, but that doesn't extend to other operations. So for example, the integral of a product needn't be the product of the integrals. So here, for example, x times x is x squared. So when you took its antiderivative, you'd be looking at some kind of x cubed. But if you break along the time sign, the integral here of x is some kind of x squared, and the integral here of x is some kind of x squared. So this side is some kind of x to the fourth. So the two sides are not equal. A similar thing happens for quotient, and a similar thing happens for composition. Okay, so when we first did derivatives, we had to go on to learn product rule, quotient rule, and chain rule. So too here, we have to learn how to take the antiderivative in those contexts. I have a couple of points I want to mention here before I close, a couple of technical points about antidifferentiation. And the first one is that the definition talks about intervals a lot. So I'm going to click back to the definition. I know the discussion is there, but I want to click back to the definition to dramatize that. It says, let the function be defined on some interval. An antiderivative is a function f so that f prime equals lower f on that interval. What's the interval talk about? What's that about? So I just want to consider that for just a few minutes. Whoops, went too far. So consider, for example, the function f of x equals 1 over x squared. So 1 over x squared. We know that it's not defined at x equals 0. So that is to say that it's defined for the negatives and it's defined for the positives, but not at 0. It's absolutely the case that one antiderivative is minus x to the minus 1 plus capital 3. If you take the derivative of minus x to the minus 1 following the formulas from the formula slide, if you take the derivative of minus x to the minus 1 plus capital 3, you will indeed get x to the minus 2. However, what's below, do you see, has a different constant for the negatives than it has for the positives. That also works. If you take the derivative of this capital F, where you have a different constant for the negatives than for the positives, I drew a graph. Can you see that the horizontal asymptote is 2 on the left and is 1 on the right? So if you take the derivative of this capital F, it also has a derivative of 1 over x squared. So the earlier antidifferentiation formulas, and also the formula that's in the book, only list minus x to the minus 1 power plus capital C. They don't list two different capital C's. Now that's usually fine, because usually when we take an integral we won't cross the x equals 0 line, but I think it's worth mentioning just in passing, just to have said that it's only fine because usually we won't cross that line. Other functions that where the same point arises are 1 over x and also ln of x. You'll remember that ln of x is not defined at x equals 0 or for negative x's either. Speaking of ln of x, so the ln of x appears in one of the antidifferentiation formulas, and here it is. The formula in antidifferentiation formula says the antiderivative of 1 over x is ln absolute x plus capital C, and there's a few things I want to describe, I want to think about the right-hand side there. I want to talk about the absolute x, I want to talk about the capital C, and I want to talk about the ln. So the whole right-hand side deserves some discussion. So first of all, the absolute value. The natural logarithm is only defined for positive inputs. We've already seen these two examples of derivatives. Saw this one that I'm pointing to now a few minutes ago. So the absolute value simply combines those two into one. It's just a convenience. Second, the plus capital C. On the previous slide, we talked about that you can have different capital C's, and indeed the same thing happens here. This is also this function capital F. This function capital F does indeed have different capital C's for the negatives as for the positives. Okay, now the book, again, as with the previous slide, the book writes ln absolute x plus capital C with a single constant. In practice, we don't usually do integrals that cross to 0, so one way to think of this is as an abbreviation. But in any event, technically speaking, you could have a different capital C on the one side as on the other side. We don't typically need that, but just to have said it. And the last one, the real reason I wanted to do these slides, the ln. So I want to look at this table of antiderivatives. Can we look at this table? So the antiderivative of x to the 1 is some kind of x squared. The antiderivative of x to the 0 is some kind of x to the 1. So you're bumping the power up by 1. Can I switch over to the left-hand side? Antiderivative of x to the minus 3 is x to the minus 2 kind of expression. The antiderivative of x to the minus 2 is x to the minus 1 kind of expression. It all fits together, and then here, one of these things is not like the others. What's going on there? What's going on there? Well, of course, if you look at 1 over x, x to the minus 1 power, if you're going to add 1 to it, you get x to the 0. So far, so good. But then when you go 1 over that number, you're looking at 1 over 0, so that's not defined. So, of course, there's trouble following this formula. Of course there is. Nonetheless, what's happening with the ln? How does that fill the gap that's in this table? So I want to look at these functions here, and I want to see how ln fits into that collection of functions. First of all, ln has a property that if you give it an input 1, ln will give output 0, whereas if you take this function and you give it an input 1, it'll give you output 1. actually output 1 over a plus 1. I don't want that. I want the two of them to line up. So I'm going to adjust this here to make it so that the term, the x to the a plus 1 over a plus 1, make that part there have an input 1, output 0. So I adjusted by borrowing some constant from the capital C. I borrowed 1 over a plus 1 from the capital C, and I rewrote now as minus 1 over a plus 1 plus capital C hat. And so now I have an expression here. I have an expression for the antiderivative of x to the a that looks a little different, but differs only by a constant from what we started with, up here. Okay, so I did a little bit of algebraic folderol at the beginning to make it fit with ln. ln, if you give ln an input 1, it will give you output 0. If you give this expression an input 1, it will also give you output 0. Okay, so having done that, now I got my computer to draw what happens as little a approaches minus 1, because it's minus 1 that I'm interested in. So what happens as little a approaches minus 1? So I got my computer to draw the graph of ln. Can you see ln in red there? And then I looked at little a equals minus a half, little a equals minus 0.9, and little a equals minus 0.95. Little a equals minus a half is not really all that close to ln. Little a equals minus 0.9 is awfully close. You can hardly tell. And little a equals minus 0.95 in dark blue, you can't tell the difference. I mean, they're practically the same. So although this is not a proof, you can absolutely give a proof, but this is not a proof. But although this is not a proof, it is nonetheless the case that when you take the limit of those functions, the limit of those expressions, the limit of the parts of the table that is not the ln part, as a approaches minus 1, you get ln. So ln does fit into that table. It's not easy to see, but ln does fit into that table. Okay, so again, try to illuminate a couple of puzzling parts of taking antiderivatives. Okay, so again, we're breaking this bank of slides up into 2 just because of length. That's all, just for convenience. So when I come back, we'll start in on the definition of the integral. Very good.